Hey, good afternoon. So let's talk about vibranium, right? Vibranium is the legendary and fictional metal that absorbs energy, defies physics, and makes Wakanda probably the most advanced nation on Earth. But what if vibranium was actually real? Where would it sit on the periodic table? What would its properties be? And how might it relate to the tantalizing concept of the island of stability in superheavy chemistry? Today I'm going to explore the hypothetical periodic placement of vibranium. Now, in the Marvel Cinematic Universe, vibranium's canonical properties include energy absorption, high strength, and unusual resilience. I'll treat vibranium as a thought experiment, a heavy metal or a metalloid with extraordinary stability and exotic behavior, and let's attempt to see how it might fit into an extended periodic table. So I'm going to walk through the theoretical basis for extending the periodic table. And I'm going to consider the island of stability and how vibranium might exploit that. And then we're going to look at some candidate periodic positions, what block would it apply to, what group, and what period might we find vibranium occupying the periodic table. And then we'll look at some predicted physical and chemical properties, and then some challenges, caveats, and some other what-ifs, right? So first, our concept of the elements in our study of matter has grown quite substantially throughout human history. We started out with the original classical Greek elements. That's earth, air, fire, and water. And then we ended up in around 1869 to Dmitri Mendelev's first periodic table with 63 elements, and scientists have recently expanded that to 118 elements that we know is our periodic table today. And of course in 2016 we've completed that seventh period with the addition of 4 new elements: nihonium, moscovium, tennessine, and oganesson. So now the seventh period is complete. And so expansion beyond the periodic table will, of course, add an 8th period and a new row just below our periodic table to our list of known elements. And so many of these elements recently added to the periodic table are only stable for a very short period of time. We're talking milliseconds or microseconds. And theoretical physicists and chemists exploring potential new elements have theorized about the concept of an island of stability. And this suggests that certain super heavy nuclei, especially in the neighborhood of maybe atomic numbers 114 to 126, might be relatively more stable with longer half-lives than their neighbors. And this is due to closed nuclear shells and proton and neutron magic numbers, right? So many of these proposed super heavy elements that decay in microseconds or less, but if an element sits near the island, it might survive seconds, days, or even more, maybe even enough to study actual chemistry. So that's where it gets really interesting. And so many educators and theoretical chemists and physicists have explored speculative periodic tables, and they've placed hypothetical elements in new periods, and that's, different rows of the periodic table. Periods are rows, columns are groups, right? And so we've postulated a G block or an extended FG block, right? And so the current periodic table is organized based on how elements would add electrons from left to right filling the s, p, d, and f orbitals. Hence, we have the s block in the the 2 columns on the left, and the p block with the 6 columns on the right, ending with the noble gases, and that has a full octet. Then the d block with 10 columns in the middle, and the 14 columns of the f block, which is just to the left of the d block. Although most periodic tables in textbooks will put this separately at the bottom, mainly to save space so the periodic table is not too wide. And so the G block is a hypothetical region of the extended periodic table where electrons would begin filling G orbitals. And so that's just as in transition metals fill D orbitals, and lanthanides and actinides fill the F orbitals. These elements have not been discovered, but theoretical chemistry predicts that extremely heavy elements in periods 8 and beyond may require G orbitals to describe their electron configurations. So this G block would have 18 elements in each row. Every element we'd add an electron to, and that compares to the 10 elements of the D block and the 14 elements of the F block. And so because vibranium is extraordinarily stable, it kind of makes sense, at least in our fiction, to consider that it might inhabit a region close to or on the island of stability. And so a super heavy nucleus, such as vibranium, would be unusually long-lived. So let's imagine vibranium placed in period 8 in the G block, and it would have nuclear properties that make it stable enough for macroscopic existence. And so here's how we might decide to place vibranium. First of all, because vibranium is super heavy, we're going to place it in period 8, and that's beyond the known elements. And so it likely belongs in the new G block. At least I'm going to put it there. Sure, yeah, I could probably put it in the S block under francium or radium. But I think based on predictions of the island of stability, as well as how Marvel describes vibranium as metallic, we should probably look at least to placing it at least at atomic number 121. Alternatively, we might extend the D or F blocks further, which would enable us to compare to other metals a lot easier in existing groups. And this would be based on various properties, because each group, each column, has different properties, very similar properties to each other. Now in this example, let's put vibranium in period 8, so that's the 8th row of the periodic table in the G block region, similar in spirit to hypothetical elements 121 to 138 or similar. I would also suggest using the chemical symbol VB. V is already taken by vanadium. So to imagine its chemistry, we can try to provide it with some relatives. Now, while placing it in the new theoretical G block does add a level of uncertainty because these elements would not necessarily be lined up with existing metals, we might consider what known metals are similar to the fictional properties of vibranium. That is, strength, toughness, density, energy absorption, heat resistance, and unusual electronic behavior. Now, some known metals that seem to have somewhat similar properties to vibranium that we know about include, well, first of all, titanium. And it has an extremely high strength to weight ratio. It's corrosion resistant, and it's tough and fatigue resistant as well. So it makes a very useful application in the aerospace industry as well as in armor. And even like MacBooks or Apple uses titanium for its things. It's lightweight and it's very strong. Now, tungsten has an extremely high melting point, 3422 degrees Celsius. It's very dense, and it has strong metallic bonding and high hardness. So it's virtually indestructible under heat and stress. So that's very similar to vibranium. And of course, osmium is kind of an odd or an exotic metal. It's the densest naturally occurring element, has a very stiff crystal lattice and strong or relativistic bonding effects. So osmium is basically an ultra-dense exotic metal. Then of course we have nickel. Nickel-based superalloys actually retain a lot of strength at extreme temperatures, and they resist creep and fracture. They also have highly engineered microstructures. So nickel is a very advanced engineered metal with very extreme resilience. So if we consider these elements, we might consider placing vibranium in the 8th period as atomic numbers maybe 122, 124, 126, or 128. This would place it near the island of stability, where nuclear shell effects could allow unusually long-lived super-heavy elements, and that gives vibration a foundation in nuclear physics. A dense, relativistically stabilized, transition metal-like element with extraordinary mechanical and electronic properties. So for the purposes of this video, I'm going to put vibranium as atomic number 124. And that's analogous to chromium, molybdenum, or tungsten in the D block, or neodymium or uranium in the F block. But we'll put it in the G block with the electron configuration of OG, 5G4, 8s2. We could also use the nuclear shell model to predict that this element should have about 184 neutrons, and this would make it a doubly magic nucleus, providing it with enhanced binding energy to its neighbors. And so if we add 124 and 184 neutrons, we would be able to predict an atomic mass of vibranium of roughly 308. And so from that placement, we might predict some of the following properties for vibranium. Extremely high density, 25 to 30 grams per cubic centimeter, metallic bonding with strong electron delocalization, would have oxidation states of +2, +3, maybe even +4. Strong relativistic effects in influencing bonding, and it would have exceptional lattice stability. Its fictional energy absorption that we see in the Marvel comic cinematic universe could be interpreted as an extreme form of phonon dampening, or maybe even lattice energy redistribution. So that's vibranium. Now let's shift a little bit and look at another science fiction story with another super strong substance, a little bit newer, and that's Xenonite. And that comes from Andy Weir's book and the 2026 movie that just came out, Project Hail Mary. And so Xenonite could actually be considered even more chemically outrageous, and that's because it's derived from xenon. Now, xenon is not fictional, that's atomic number 54, but it's a noble gas. And noble gases are supposed to be chemically inert. Now, in reality, xenon's kind of lower in the periodic table, and with 54 electrons, it can actually form multiple compounds, mainly compounds with fluorine and oxygen, highly electronegative elements, such as xenon hexafluoride or xenon tetraoxide. These occur because xenon is heavy enough that its electrons are a lot more polarizable, and it has ionization energies that are a lot lower than many of the later noble gases. And it also has relativistic effects that are going to stabilize bonding as well. But these compounds are actually highly reactive, they're often unstable, and they're definitely not structural materials. And so in the book, Xenonite is a fictional, ultra-strong, versatile material It's engineered by the alien character Rocky from Eridia, from Erid. And so he used xenon to build. It's the primary construction material for Eridian technology. They built their ships and multiple tools out of xenonite, and it's notably capable also of being transparent, as depicted in the movie as well. And so its properties include a very high tensile strength, the ability to handle extreme heat and pressure, and it can exist in various forms, from a very rigid, opaque materials to transparent glass-like sheets. And so the material is manufactured by combining two liquids similar to an epoxy. And so the protagonist in the movie, Dr. Rowan Grace, actually coined the term xenonite because it appears to be a compound primarily made of xenon, although it actually behaves more like a very robust engineered form of plastic. Now, to turn xenon into xenonite, you would need an extremely high pressure, much like you would see on Erid with the Eridians living under an extremely high pressure. This forces the xenon atoms to be into very close contact, and it allows them to overcome closed shell repulsion. You would also need orbital hybridization beyond normal chemistry. And so this is possibly involving multi-center bonding or maybe partial electron delocalization, which you see in metal-like behavior, right? You would also need a stabilization mechanism. You would need continuous high pressure, such as you would see on Erid, or maybe some sort of exotic bonding, which, I don't know, that's unknown to current chemistry, so who knows where that would come through. This, again, we're talking science fiction here, so let's use a little imagination. Now, here's the key difference between vibranium and xenonite. Of course, vibranium would be a whole new element occupying the 8th period in the periodic table. And of course, xenonite would be a new phase or an allotrope of an existing element. So xenonite doesn't get a new box on the periodic table. It's already there. It's a noble gas. It's atomic number 54. Instead, it represents something like a high-pressure condensed phase of xenon with extended bonding. Now, these two materials highlight two orthogonal frontiers in chemistry, right? First of all, vibranium breaks the nuclear frontier, right? And so that involves stability determined by proton-neutron shell structure, and the chemistry emerges after its nuclear viability. Xenonite breaks the electronic frontier. Xenonite, of course, has the same nucleus, and we have entirely new bonding under very extreme conditions. So again, a different thing. We don't have to create a new element on the periodic table. We already have xenon. We're just kind of applying different chemistry and different physics to xenon to make xenonite. So if you wanted to place them on the periodic table, vibranium sits far beyond it. We're going to have to add period 8. Xenonite doesn't really move at all. It redefines what xenon itself can do. So one expands the periodic table, the other breaks the rules within it. So which is more plausible? A stable element 124 or a structural noble gas? If we ever discover the island of stability, what would our version of vibranium look like? Why don't you let me know in the comments down below. See what you think. See what you're thinking. We could go multiple ways with this. Now, if you're interested in exploring some of these fictional elements a little bit further, I'd recommend, of course, reading Andy Weir's book, Project Hail Mary. The book actually goes into some of the actual science in a lot more detail than you would expect to see in the movie, obviously. He does a really good job of going through the science and explaining complicated things. For more information on vibranium in the periodic table, I'd recommend taking a look at this paper in the Journal of Chemical Education. And this paper is by Sabrina N. Collins at Lawrence Technological University. And she actually posed this as a potential question in general chemistry classes to first-year students. And just thinking about a fictional element on the periodic table and where that would be. And so that was an interesting class assignment that kind of came up. So once again, thanks for watching, and I hope you enjoyed the video. Go ahead and hit the like button and the little bell icon so you're notified when new videos are posted. And thanks for watching.